Hey guys, welcome back. This is going to be the beginning of the notes for circular motion and rotation for APC. Looking at what I wrote, this is about 30 learning objectives. It's about 20% of the entire course, and it is almost always a free response question. So it had a 10-year streak in a row where it was a free response question, and it's been a free response question 20 of the last 21 years. There's been some kind of rotational one. You guys have copies of these, so you can go over those and read it. And they put circular motion here too, which kind of makes it seem like that's why there's so many extra. All right, so I'm going to bounce through this pretty quick and get to the calculus parts because we've already covered this once. So in rotational motion, we're going to have our angular quantities. We're going to have distance is going to be related to angle measure. Velocity is going to be equal to or related to angular velocity. Acceleration is going to be related to angular acceleration. F net equals ma is going to be related to the sum of our torques is equal to I alpha, and so mass is related to our moment of inertia. Torque is going to be the cross product of how far we are from the lever arm and what the applied force is perpendicular. If we have constant angular acceleration, then our problems for constant linear acceleration, we'll just switch out those for rotational problems. And all I'm missing now is momentum, I think. So probably the next slide. Oh, kinetic energy. So we're going to have kinetic energy linearly is going to be 1/2 mv squared. Rotationally, it's going to be 1/2 I omega squared. Angular momentum, we have linear momentum is equal to m times v. Angular momentum is going to be the vector cross product of r cross p. And again, the order of these matters. P cross r is not the same as r cross v. This is going to be conserved if there is no net external torque. And then we're going to get our vector direction by doing right-hand rules. So those are going to be perpendicular to the two vectors that we combine. Like I said, I'm going to jump through this. All right, so on your equation sheet, we have centripetal acceleration is rewritten as v squared over r or omega squared over r. And they do write down that linear velocity is equal to the radius times our angular velocity. Again, this is a non-slipping situation. So this doesn't work if you have something that is slipping. We have frequency and we have period. Here we have our angular and our linear, which I wrote down on the first page. Rotational kinematics. We have the equivalent of the V equals V naught plus AT, and the X equals X naught plus V naught T plus 1/2 AT squared. We're missing the V squared one, but you would just have to replace the values. All right, so a cylinder rotates with constant angular association about a fixed axis. The cylinder's moment of inertia about the axis is 4 kilograms meters squared. At time t equals 0, the cylinder is at rest. At times t equals 2 seconds, the angular velocity is 1 radian per second. What is the angular acceleration of a cylinder between t equals 0 and 2 seconds? So my initial velocity is 0. My final velocity is 1. I want to know what my acceleration is, and they give me time. So omega equals omega naught plus alpha t. And so we have omega divided by omega naught over t, which is going to be 1 divided by 2. This one requires calculus, very much like we could go from displacement to velocity by taking the first derivative and velocity to acceleration by taking the second derivative. We can do the same thing for our angular values. So we have an equation where theta equals 3t squared plus 2t. What's the speed at 4 seconds? So this is going to be the derivative of theta with respect to t. So this is going to be 6t plus 2. And then if you put in a 4, you would get that it's 26. So pretty straightforward, but a little bit of calculus. Turntable that's initially at rest is set in motion with a constant angular acceleration alpha. What is the angular velocity of turntable after it's made one complete revolution? So one complete revolution would be 2 pi radians, right? Not 2 pi r, 2 pi radians. And so we would have that omega squared equals omega naught squared plus 2 times alpha, theta minus theta naught. So I have omega is going to be equal to the square root of 2 alpha 2 pi, which is the square root of 4 pi alpha. So torque is going to be our lever arm times our force perpendicular. The way we write this, in vector algebra is the vector cross product. The cross product of 2 vectors combines their perpendicular components and gives you a resultant vector. As opposed to the dot product, which combines parallel components and gives you a scalar. So here's how it's written on here. And again, the order of this matters. It also appears there in terms of the second law. All right, a rod of negligible mass is pivoted at a point that is off center, so the length L1 is different from L2. The figures above show 2 cases in the mass are suspended from the ends of the rod. In each case, they're balanced. What is the value of M? All right, so that means we're doing that the counterclockwise torques equal the clockwise torques. So I'm going to have mg L1 is being balanced by m1 g L2. And I'm going to have that m2 g L1 is being balanced by mg L2. I'm going to get rid of the g's. And so m is equal to m2 L1 over L2. M is also equal to m1 L2 over L1. So I think I want to substitute in one for L1 or L2. So why don't I say that L1 equals M1 L2 over M, and I'll put it in for L1 there. And so I'm going to have M2 M1 L2 over M L2 is equal to M. And then I can cancel out an L2, multiply M over here. So I have M squared is M2 M1. So M would be the square root of M1 M2. I thought I could set it equal, but that wasn't going to work. So I do a substitution. Which defined diagrams the torque about point 0 equal in magnitude of the torque about point X in the diagram above. The torque would be F times L because those are perpendicular. So I need to find something that is worth equal to F times L down here. This has no torque. This one would be FL over 2. I don't know why we're at R. If this is 30, then this one would be 2F cosine, right? Because the adjacent side would be perpendicular. Cosine of 30 times L, which that's not 1/2. So this would be cosine of 60, which that is F. So I would have 2F cosine of 60, which is 1/2. So 1/2 times 2 is 1, so it's C. Torque is a rotational analog of force. So if I'm pushing there, I would want to balance it by pushing it there. So I would be balancing it both linearly and rotationally. We have torque problems. This is just balancing things out. I have the bigger mass here, so I'm going to want to be closer to the bigger mass. So it's going to be D. Right, and 1, 2, 3 times 8 is 24, and 1, 2, 3, 4 times 6 is 24. So that would balance. All right, so we can write the second law as the sum of the torques equals the moment of inertia times our alpha. This is how it appears on your equation sheet. Instead of writing it as F net equals MA, they're rewriting it as A equals F over M, where our alpha would be our rotational acceleration. We have the sum of tau, or we have tau net divided by I. And I have a separate set of notes on showing how to do the derivatives. I did the hoop for you. I did a disk for you. And I did various different rods, both with calculus and with the parallel axis. But this is I equals the integral of r squared dm, or generically it's a sum of mr squareds. Here are some that we just know. If we have a hoop, we know it's mr squared. If we have a disk, we know it's 1/2 mr squared. If we have a solid sphere, we know that it's 2/5 mr squared. If we're doing it through the center of something, we see that it's 1/12 ml squared. And if we're doing it about the end, we see it's 1/3 ml squared, as I write 1/3 ml cubed. So you should be familiar with those. In rotational dynamics, it's very much like solving F-net problems. The big difference is that we also have to have the lever arm, so how far it is away from the axis. And we did these already in the notes. So, light rigid rod with masses attached to its end is pivoted about a horizontal axis shown above. When released from rest in horizontal orientation, the rod begins to rotate with angular acceleration of magnitude. So, the sum of our torques is going to be equal to I alpha. So this is going to be torque counterclockwise minus torque clockwise divided by I is going to be equal to alpha. So the counterclockwise torque would be the weight of this one. So that's going to be 3 m naught g times L minus the clockwise torque, which is going to be 2 m naught g L divided by the moment of inertia of this. These are going to be generically mr squared. I need to change colors. So this one would be 3 m naught L squared, and this one would be just m naught, but it's 2L squared. So up top I have m naught GL. At the bottom, I'm going to have 3 m naught L squared plus 4 m naught L squared, which is 7. So I have m naught GL over 7 m naught L squared. I can get rid of an L, get rid of an m naught, and I have G over 7L. That's a good example. We hadn't done that one previously. The parallel axis theorem, and I covered this as well in a separate video where we just covered the parallel axis theorem. But if you know what the moment of inertia is, you can calculate what it's going to be at a parallel axis just by taking that original moment of inertia and then adding the mass times how far we're moving in parallel squared. So uniform stick has a length of L. The moment of inertia about the center of the stick is I naught. A particle of mass m is attached to one end of the stick. The moment of inertia of this combined system about the center of the stick is. So this would be equal to I naught plus, and we're saying that we're just sticking it. So that would be, that's actually not a parallel axis one. We're just adding the two moment of inertias together. One of them is mr squared and one of them is given to it. Because we're not moving it, it's still about the center. This one we are moving it. Uniform thin rod shown above is a mass m and L. The moment of inertia of the rod about an axis through its center perpendicular to the rod is 1/12 mL squared. The moment of inertia the rod about an axis perpendicular to the rod passing through point P, which is halfway between the center and the rod. So how much did I move it? I moved it by a distance of L over 4. And so this is going to be M D squared, where D is going to be L over 4. And I think I did almost exactly this example in one of the videos. It seems really familiar to me. So we need to get a common denominator, which is going to be 48. So I'm going to have 48 ml squared plus 48 ml squared, which is going to be 48 ml squared. So that's an easy way to do it, but they will ask you to do it in calculus sometimes. It's just they want to see that you can do the derivative, which is very straightforward with this, as long as you pick the points you're integrating across carefully. All right, rotational kinetic energy is this 1/2 I omega squared. Again, just showing you where it shows up on the equation sheet in case you need to look for it. This is just a plug and chug, right? So they give us the moment of inertia is 4, and they give us the angular velocity is 1. So it's just going to be 2. Tricky thing with rolling things is that they're not losing any energy due to friction when they're rolling down. I think we conserve energy. All right, so a bowling ball of mass m and radius r, whose moment of inertia about its center is 2/5 mr squared, rolls without slipping along a level surface at a speed v. The maximum vertical height which it can roll if it ascends to an incline is. So we're going to have 1/2 mv squared plus 1/2 I omega squared is equal to mgh. And I need to plug in for I, which is 2/5 mr squared, and omega, which is v over r squared. All right, I'm going to cancel some stuff. I'm going to cancel m's. And I'm going to cancel r's, right? Because I have r squared down here. I have r squared up there. And I'm going to cancel it too. So I have 1/2 plus 1/5, which would be 7/10 v squared equals gh. And so h would be equal to 7/10 v squared over g. So work can also be written as the torque times the change in angle, and I derived that for you guys in a previous video. Our angular momentum can be written as the moment of inertia times our angular velocity, or the cross product of the radius and the linear momentum. This is going to be constant if there is no net external torque. This is useful in a lot of orbits problems. So when we're dealing with a comet going around something, you can conserve energy, but conservation of angular momentum makes our lives so much easier. And this is where it's written. Again, this is a vector cross product, so the order of these matters to what the answer is going to be, because it'll affect the direction when you do the right-hand rule. And I did these demonstrations with you guys, and I did that problem. All right, so a satellite S is an elliptical orbit around a planet P as shown above, with R1 and R2 being its closest and farthest distances. If the satellite has a speed of v1 at its closest distance, what is the speed at its farthest distance? So we're saying that our moment of inertia times our angular velocity. So our moment of inertia is going to be mr1 squared. I can rewrite my angular velocity as v1 over r1, and I can do the same thing on the other side. Switching out our subscript of 1s with subscript of 2s. And what happens is that we end up with that the masses cancel because the satellite's not changing its mass as it orbits. And one of the r's cancels. So really, all we're left with is r1 v1 is equal to r2 v2. And so if I want to get v2, I would divide r1 v1 by r2, which is choice A. Elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest and the nearest position to the sun. And at a position 1, the distance from the comet to the sun is 10 times that at position 2. At position 2, the comet's kinetic energy is the maximum because it's going to speed up. That's its closest distance. So what is the ratio of v2 to v1 of the speed of the comet at position 1 to the speed of the comet at position 2? So I'm going to have m1 v1 r1 is equal to m2 v2 r2, and the m's are going to cancel. And we're saying that position 1 is 10 times that of position 2. So I have 10 r2 is going to be equal to v2 r2. So v1 over v2 is going to be r2 over 10 r2, which is 1 over 10. And again, I simplified this down from the I omega squared, just like I did in the previous slide. So that makes your life easier. A moon of mass m orbits a planet of mass 49m in an elliptical orbit as shown above. When the moon is at point A, its distance from the center of the planet is RA and its speed is v0. When the moon is at point B, its speed is 5 v0. When the moon is at point A, the distance from the moon to the center of the mass of the planet of the moon is system. So center of mass, so I'm going to be here. It's going to be m times 0 plus 49m times RA over 50m, right? It's the mass times the position plus the mass times position over the sum of the masses. So that looks like it's going to be 49 over 50 RA. What's our distance going to be when we're at B? So again, it has to be MA, RA, BA equals MB, RB, BB, and the masses are constant. And so if we're saying that its speed is 5 times as much, it needs to be a fifth of the distance because there's no net external forces in this. All right, to find out the direction, we do the right-hand rule. You put your fingers in the direction, you curl your fingers around. So as this is spinning around this way, I curl my fingers, and the vector direction is straight up. And I showed you guys this with the precession, with the grinding wheel. All right, so angles are measured in radians. A circle all the way around is going to be 2 pi radians. All this is just review. I think we're good. We talked about friction. We talked about frequency. We talked about torque. All right, I think you guys are ready to try some problems.